The definition starts out section 5.1, and that is a probability distribution. So when we talk about probabilities, a lot of times we have to have a means to tell you, well, how likely it is that you get a certain outcome. Now that certain outcome is a random variable. It's typically represented by X, and it has a numerical value determined by chance. Now that's a big thing for us. It has a numerical value. So keep that in mind as we answer some of the questions below. The probability distribution that's associated with that random variable is a description of where the probabilities occur and what each probability is. It's either a number or a formula or a table. But let's start by looking at these questions here. Determine whether the value is a discrete random variable, continuous random variable, or not a random variable. So one of the things to keep an eye out for is that it has to have a numerical value. We'll start with part A. Number of points scored during a basketball game. Well, points at least is a number, so it's a random variable. Is it a discrete random variable or a continuous random variable? Discrete, because you can't score in a basketball game anyways half of a point or a quarter of a point or something like that. So this is a discrete random variable. Let's keep going. The time it takes to fly from city A to city B. Well, a lot of things can affect that, but it is a number, so we got that going for it. It's determined by chance, maybe the wind, the traffic patterns around the city, other things like that, so it's determined by chance. Is it discrete or continuous?
Continuous.
Continuous.
You chose discrete.
The eye color of people on a commercial aircraft flight.
Not.
That's not a random variable. It has to be a numerical value. The time it takes for a light bulb to burn out.
Continuous.
Continuous. The number of statistics students now reading a book.
Discrete.
Discrete. Good. You can't have partial of a student reading a book, so it's discrete. And the number of free throw attempts before the first shot is made. Discrete. You can't have, a partial number there. So it's going to be discrete. In another class, you might go a little further in studying that. That would be what's called a geometric random variable. Let me remind you about probabilities. Probabilities have to be between 0 and 1. On the test you're getting back today, a lot of people give me values outside of that. And as I said before, you're kind of making it easy for me to grade. But let's take a look at the spreadsheet that I gave you here, and it's reproduced for us here. We want to decide, is this a probability distribution? So Jackson, there's two things that I need to figure out if it's a probability distribution. First of all, are these all legitimate probabilities? Yeah, they're all between 0 and 1. And the second thing is that we need to see, do they add up to what? What do you think they should add up to? Should add up to 1. Now, you could sit there and punch these in on your calculator, but this is why we're using Google Sheets. It's going to make this a lot easier. Type in equals, and then, you know what, how come this is not letting me do this? Oh, one thing you might need to do so that you can edit this is you might want to make a copy. Make your own copy, save it to your own Google Drive account. That way, when you get home and you want to look back at things, you can. You'll have a perfect copy that you made. Now, let's see. Here, this is the one that I own, I think. Equals sum, and then you want to click and drag up here, you should get exactly 1. Now, sometimes depending on the example, maybe you get 1.001 or 0.999. Okay, all right, kind of wink and nod at that. They should total up to 1 to be a probability distribution. But if they're really close but not exactly on, then all right, we'll just kind of let it go. If I were to give you an example of something that wasn't a probability distribution, I'm going to make it kind of obvious. I'd make this like, I don't know, a 5, something like that, so that it totals up to 1.3. That's not close, all right? But if you get something that totals up to, 1.002 or 0.998, all right, it's probably meant to be a probability distribution. So the answer here is yes. Yes. And you could say it fancy, the sum of the probabilities is 1. That's kind of a fancy way to do this.
So basically, we're looking to make sure each value is between 0 and 1, and then also they add up to approximately 1.
Exactly. You're looking to make sure each value is a legitimate probability between 0 and 1. And the second thing is that they add up to 1 when you total them all the way down. Perfect. Now the next one, they're trying to make a little bit more of a point of this, and this is going to become something that we're going to concern ourselves with later on as well. And that is, let's take a look first of all at some probabilities. Probability that if you're trying to get 2 flips to be heads out of a total of 4 flips, there's a 37.5% chance that that can happen. What about getting 4 heads out of 8 flips? Well, now that chance diminishes. Now it's 27%. And you keep on increasing the X and the N, 10 flips out of 20, 50 flips out of 100. What's happening to these probabilities if I keep on increasing the value of N, the number of coin tosses here? What's happening to these probabilities? Yeah, go ahead. Yeah, it's getting smaller. Now, do you remember what our cutoff was for something to be significant? What was it?
5%.
5%. So if something has less than a 5% chance of happening, then we say, oh, well, that's significant, all right? Because 5%, and less, that's kind of on the rare side. And part of the point of this problem here is that an event can be rare just by increasing the number of flips here. So if I increase the number of coin flips up to 300, even though on average I might expect 150 of them to be heads, that's not really a surprising or shocking event. But according to our 5% rule down here, this would be significant. So what I'm saying is that we got to think of this a little differently. We can't just think of this one probability happening. We've got to think a little bit more. And what the author is suggesting is that we don't just think of a probability of, say, 58 girls out of the next 100 babies. We look at the probability of 58 or more girls to try and find out how unusual something is by looking at what's called the tail of the distribution. Now let me graph this for you up here. Let me make that 1. No, let me go back and make that a 2. I'll just keep it as a 2. So I could look at, for instance, the probability of getting 1 occurrence of something. Right now, that probability is 0.0208. By our definition, that's less than 5%. Ooh, that's rare. But what the author is saying is like, you know what? We're going to look at getting this event or something more extreme, which would be all this area out in the tail. So instead of just looking at the probability of x equal exactly 110, what if I go up to, I don't know, 200? Getting all these probabilities. So I went from a probability of like 2% to a probability of like 9%. So I'm getting all the area in this tail. And when I add up all the area in that tail, you know, probability of getting something of 110 or more isn't all that rare. And that's what we're going to judge things on in this class is what's the probability of getting something like this or more extreme. So the click down menu here, the drop down that you're going to get when you do your homework is going to give you a couple choices. And the choice that you want here is going to be the probability of 58 or more girls. 58 or more girls. So that's what you're going to put in the drop down menu in the first one. Now the probability of 58 or more girls was 0.067. Does that meet our criteria of being significantly high? If the probability is 0.067? No. Because in order to be significant, its probability has to be less than 5%. So this is not a significantly high number of girls because the relevant probability is blank compared to 0.005. Yeah, more than, greater than, you know, either one. Oh yeah, it's greater than 0.05. Hey, and that's it for that one. Okay. These, let's see. This should be, the handout here should be on D2L in the handout section. Let's look over here at example C, throwing a pair of dice. And let's kind of go back and do our counting rule as well from the first section that we covered today, section 4.4. How many possibilities are there for rolling the first die? How many, when you roll a die, there's 6 possibilities. How many possibilities are there from rolling the second die?
6.
6 again. So you give a total number of possibilities of 36. And that's how many possibilities you see right here. That's the number of points in this thing. Can anyone give me a name for this thing? Oh, well done. That's your sample space. So it's 36 points in the sample space. And from there, you can figure out your probabilities. Like there's 1, 2, 3 different ways that I can roll a 4. So I've got that listed for you here. X is the number 4. There's 3 different ways you can roll that. 3 out of 36 turns into 0.0833. And so on. What's the most likely roll that you're going to get when you roll a pair of dice? 7, right? Because 7 can occur in any of 6 ways. So you've got a 1 in 6 chance of rolling a 7 with a pair of dice. But we're going to go a little bit beyond that, and we're going to look at what the average roll is. If you were to roll a pair of dice thousands and thousands of times, on average, what are you going to get? Well, let's take a look here. So let's go to our Google Sheet. This should be for 5.1, example C. You should have some stuff that's already in here. Is that true? So here's your X. Here's its probability. And all it is just 1 out of 36. And 2 out of 36, etc. You can see the most likely roll here is a probability of 1 out of 6, etc. This is a probability distribution. Notice that it adds up to 1 exactly. If you take a look here, I'm summing up these numbers and I get 1. It's all that on your sheet there. All that on your Google Sheet coming through? Thank you. Suppose I want to figure out what the average roll is. Basically, something that I'm going to call mu, or the mean, or the expected value. So it has a lot of different names, but we're going to call it the expected value. So this is going to be your expected value. It'll also be called the mean. It's also called mu. So there's 3 different names. This is what's going to happen on average if you're rolling a pair of dice thousands and thousands of times. What's the average roll? Now, it doesn't always have to happen that the average is actually a number that you can get. If you had a pair of unfair dice, you might get an average of 4.5, even though you can't roll a 4.5 with a pair of dice. That's okay. We don't need that. To get the expected value, you're going to take this column, which is your x, and multiply it by p of x. So this times this. So let's do that here. Let's click equals. Let's see. I want this times this. So it should be B4 times D4. That's what should be in your cell E4. I want equals B4 times D4. And when you press enter, it should change it to that. Now, I'm going to repeat that calculation down here and here and here. In fact, let me just get rid of these real quick. So I'll just highlight them, hit the delete key. There's a couple ways I can repeat it. I can copy this cell and paste them down to here. But the easiest way to repeat this is with this little box. It's just to drag it all the way down. And you should get something that looks like that. Now let me go back up here to make sure that you have the correct initial calculation. So in this cell, it should be equals B4 times D4. Once you have that, drag all the way down. You should have a distribution, or at least a table that looks like this. The sum of these numbers is your expected value. So to get those, Creedy, we're going to hit the equals key and then sum them up. Sum. Once you type in the command sum, click, drag, and highlight all your characters or all the things you want in your sum. What are you getting when you type all those in? You should get a nice round number when you type those in if you're getting it right. So let me walk around and see who's getting it. Equals, and you want the sum of those. Did you redo this calculation all the way down? No, that should.
Yeah, I got 14. This one's supposed to be 7.
Your numbers
There's a
got
copy. It'll be B4 times D4 is what's called 1, and then drag it down. these numbers changed, so I did the sum. I'm not sure.
Supposed to be 7?
Let me make sure I get a 7.
I
think
got
that's
7.
what some-
I got 4.0.
Yeah, some people are getting 4, some people are,
It was 7 with the numbers that were given, but once we did it,
You gotta
It was
scroll
4.
over to the left some more, I think you multiplied the wrong thing.
you know what? I think I did too. I might have multiplied the wrong things here. Yeah, because I'm getting 4 here. I wasn't over far enough. All right, so let's try that again. All right, so my bad. Equals. And I should have had A, and then asterisk, the time symbol is above the number 8, so shift 8 times P of X. And you want that from D. Now let's copy that all the way down. And there we go. Now we get exactly 7. Perfect, that's what we wanted. Nice. So that's the average roll. Now we're going to use the average to try and determine a couple other things here. But are you able to get mu here? This is mu. So mu, Greek letter mu. That's the average. We're also going to determine the standard deviation. And what good is a standard deviation? Well, the standard deviation is useful, much like our 5% rule is useful. It's going to help us determine what's typical and what's not typical. So, in terms of what's typical, in terms of what's typical, it's typical that most of your values lie within 2 standard deviations of the mean. Let me scroll down to that here, right here. Your range rule of thumb for identifying significant values. Values that are below 2 sigma, 2 sigma below the mean or lower are significantly low, and 2 sigma above the mean are significantly high. So this is a different way to look at high and low values based on a distribution. Let's see, let's go back to this and find the standard deviation. There's 2 parts to find the standard deviation. The first part, we're going to find the variance. The second part, we're going to find the standard deviation. Standard deviation is the square root of the variance. To find the variance, here's our calculation. We're going to do P of X times X minus mu squared. That's the calculation I want to put in this first cell. So stay with me on this, because I want to get that first cell right. The rest of them we're just going to copy. So come up to cell F4 and let's type equals. P of X, that's in column D. So I'll click this, it gives me D4 times left parenthesis X. Where am I going to find X? What column?
Roll A.
A. So click this cell A4, minus 7. Now for this part of it, you want to type in the number. I'm not going to try and go through the details. I'm not trying to make you an expert with spreadsheets. Just type in the number on this one always when you're doing these things. Right parenthesis. If I want to square things, I'm going to hit the shift key and then the number 6. Shift 6 gives you that up arrow, and that's going to allow you to square it. So you should have a calculation that looks like this. So D4 times parentheses A4 minus 7, parentheses raised to the second power. When you press the enter key, at least for me, it's offering, oh, do you want to do this calculation all the way down? Well, sure, knock yourself out. Do it for me. Why not? So I'll select this for the autofill. to get the variance here, I want the sum of these things. Now this formula here is already a sum of what's above. So I'm just going to grab this little square here and drag it one to the right. And it's going to do the same thing for me. It's going to sum up these numbers. You can just type that in directly if you wanted to. You can do equals, sum, and then click and drag. And you should get a number about 5.8, I think.
Could you go back to F2? F4.
F4 should look like this. Equals D4 times parentheses A4 minus 7 parentheses raised to the second power. Make sure you type in the mean, just the number. Don't click down here. It'll mess up your formulas. Okay. So, let's see, undo. You should have the variances 5.38 or 5.833. If you want the standard deviation, you need to take the square root of the variance equals SQRT parentheses, that's your square root, equals the square root of what we had above. So there you go, 2.4 equals square root. So the command is up here if you want to take a quick look at it. Let's see. All right, is everyone able to get this number here for your square root, the standard deviation?
Yes.
Standard deviation here tells us a lot about, it tells us kind of the same thing here as to what the standard deviation did for data. It talks about how spread out the data is. It's going to help us identify what's typical and what's not typical. So in this particular case, I want to find, well, in general, I want to find what's the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. So in this case, the mean was 7, so I'll do equals 7 minus 2 times. And you know what? I don't feel like typing in the standard deviation, so I'll just click this right here. So that's going to be mu minus 2 sigma. And then we're going to have to repeat that to mu plus 2 times sigma. So here's the minus. Here it is again for plus, equals 7 plus 2 asterisk. Asterisk is above the 8, so shift 8. And then click the standard deviation again. So we get 2.17 to 11.83. Let's look at what that means in terms of our distribution, in terms of the possible values. Here's the possibilities when you're rolling a pair of dice. 2.17 falls here, 11.83 falls here. So anything to the left of this, that's going to be unusually low. Anything to the right of this is unusually high. And if you look back at the probabilities, that would make sense. The chance of this are like less than 3%. Chance of this is less than 3%. So, okay, great. So calculating mean and standard deviation is certainly something you should practice. I'll end it up with one last example. You can do example F at home. Example F is already done out for you, or at least partially set up. Let's see here. Yeah, example F. Kind of remind you how to do this calculation. You're first going to sum this and get the variance. Then you're going to take the square root and get that. You can do your plus or minus here. I wanted to look at the Michigan Lottery real quick here. Keno's run by the Michigan Lottery. You've got all these different games with all these different expected values. Notice that one of these expected values, actually, one of them is really good and one of them is really bad. Does anyone know the significance of the negative with regard to playing the Michigan Lottery's game of Keno? You're betting $1 and trying to match, certain numbers that they pull out of a jar of 80 numbers. They're going to pull out 20 numbers out of their 80 possible. You choose to try and match 4 of them. And you get an expected value of negative 0.0916. That's for a $1 bet. What's the negative mean here in this? Does anyone know? It means you're going to lose. It means on average you're going to lose. So for every $1 bet, on average you're going to lose 9 cents. Which of these games would you choose to play if you had to play one of them?
That one.
I'd choose the 4 spot. Because you're not losing as much here as you are down here with the 10 spot. 10 spot is like 3 times as bad as this one. Here you're losing about 28 cents per play. Here you're only losing 9 cents. So in any Vegas game you play, there's going to be a negative expected value. What you would want to do if you're careful about your money is try and choose the game that minimizes this expected loss. You're going to expect to lose, and if you stay there long enough, you will lose. But if you choose correctly, if you choose a good game, then you can minimize that expected loss. All right, I'm out of time. Sorry I ran a little bit late. I will have to extend this homework. I will also extend section 4.3 as well.
So we are finished.